Okay, we akan continue into the temperature measuring device. Okay, so basically, this part of the lesson, we will look into how the observable heat energy can be measured. Okay, which range from the highest heat energy at 200 million degrees Celsius up to negative 270 degree Celsius. Basically, thermal sensing, the motivation is to create or to have change in voltage or resistance based on the changes of the measured temperature. Okay, so why this important? So in many application, there are you will see uh, where temperature is one of the most measured parameter in the industry or even in our daily life. Heat may represent the level of health of our body. For example, okay, uh, heat will depend on the time or how we cook, and also the heat will determine the comfort level where we staying in certain condition. So these are some of the thermal sensor fixture that we use to fit in the thermal sensor. Okay, I'm not going to look into this in details. So temperature sensor can be classified into contact or non-contact application. Uh, for example, contact temperature sensor, there are thermocouples, uh, resistant thermal detector, okay, RTD, thermistor, okay, uh, glass thermometer like you can see on the left, based on the indicators or level of the liquid which expand proportional to the increase of temperature. Okay, so contact sensor require the direct access to the object or the environment that we want to measure. Okay, and also we have a non-contact temperature sensor based on the radiation emits from the body or from the object or or from the environment. So we look into some of the application here. So these are the comparison, between the contact and non-contact methods. For example, in term of the condition, the contact method, we must have the direct access to the object, where some contact must be made so that the heat energy can be transferred to the sensing element. Okay, and no changes should be introduced in the temperature of the measured object. Okay, uh, means that the measuring device must not induce counter counter condition where, for example, it increase the object that we want to increase the temperature of the object we want to measure, or absorb too much of the temperature. So it must not it must quickly reach the equilibrium state. So whereas it is not does not interrupt or does not change or adding or reducing the thermal energy of the object we want to measure. Okay. For non-contact is the contact with the measuring object is indirect, but basically it must be inside. Whereas for non-contact, the measurement uh, must be facing directly to the object. Okay, or depending on the application, some application it can measure the heat even beyond thick wall. So thermal image, for example, temperature still can be measured, but the measurement for non-contact must be facing, must be facing the object. Okay, otherwise it may not make any measurement or cannot make a proper measurement. So in terms of the range for contact, the measurement above 1.2 K degrees Celsius are difficult. Okay, more than 1.2 K or 1,200 degrees Celsius. Okay, it's basically will for contact. It's basically may have effect on the structure of the measuring device. Okay, in somehow it may at some point melt or broke or change the material of the measuring device. But measurement below 1,000 degrees Celsius is feasible, for contact measurement. For non-contact, large error basically is made when we measure below 100 degrees Celsius. Okay, so we are discussing about the industry application. Okay, of course, there are thermal sensor that can measure accurately beyond or below 40 degrees Celsius, like the thermal scanner that we have at the entrance of any outlet or shopping mall, offices. Okay, even we have the handheld, so that it can measure below 40 degrees Celsius accurately. But in this case, we are talking about in industry standards. So in any industry standard device, okay, we used to measure for non-contact, measure may have some large error. Okay, and then the accuracy for contact is normally 0.5 to 1% of the, depends on, in this case, I expect that 0.5 to 1% of the measurement. Okay, measurement. So at range of 0.101% is possible depending on the measuring condition. Okay. For non-contact method, the accuracy can be around 20 degrees Celsius. It's quite large. But for in non-contact method, we usually measure very high temperature. So 20 degrees Celsius is a small fraction of the true value that is being measured. As well for uh, response time. Okay, for contact method is slow. It may take 1 or 2 minutes because for contact method, okay, we need it need times for the thermal energy to properly transferred to the sensing element. So it take 1 or 2 minutes or so. So for contact method, basically we need to give some time For the measurement to reach its final value, okay, we cannot immediately take measurement for contact methods. For non-contact, is generally very fast because it is based on radiation emit by object, thermal radiation. Thermal radiation that travels across uh, the room, okay, the space, which basically travel at the speed of light. So non-contact method basically we usually use to measure very hot or hot object. So the measurement may take at a significant distance. Okay. However, okay, the response time or the speed is not that large. Okay, that is the comparison between the contact and non-contact method. Okay, so some of this, for example, uh, an example in the paper mill, okay, where points that you can use for example, in this case, you are required, okay, to replace, okay, the new temperature transducer on the paper mill. So something that you can use as a guide in replacing the temperature transducer. So like for example here, what has been specified, okay, to fill each space means that at the spot of the installation, okay, what is the specification, what are the requirement. So remember in the last lecture we discussed about the installation type, intrusive, non-intrusive, okay, uh, and then also the installation type, whether you can use this um, large or small dimension. Okay. And think this all have been discussed in the last lesson. For example, accuracy and linearity. Okay, in the measurement. Okay, how good is the accuracy should be? How about the linearity? Linearity versus the temperature range. Okay, so that one of the things that you can consider. Okay, or you can use thermocouples. Okay, thermocouples is relatively cheaper than RTD. Okay, but yeah, of course, it uh, it 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 comes with some requirement of, for example, thermocouple. The output signal is relatively low, so you need signal conditioning. Okay, you cannot uh, easily or directly use the output, okay, into the logic solver, for example. Okay, uh, so these are other requirement that you need, you can consider. Okay. um, and the application of thermal measurement non-contact, this is another uh, device, okay, which is used in industry or avian inspection. In this case, radiation thermometer is used to check the status of a pitot tube on an aircraft. So basically, an aircraft, they have what is called as the pitot tube. Pitot tube is normally installed at the front somewhere in the front part of the airplane. So let's say, okay, when the aircraft has landed, so technician must come and check the condition of the pitot tube. So if they want to check the operational of the pitot tube, one way they have to use a riser, okay, or crane, okay, that allow them to look into the pitot tube immediately. And one thing that they want to check the pitot tube is the uh, safety or the hello. Yes. uh, okay.
Yes, sir.
Yes.
Doc, I can't see the video, sir. I can't view it. The lecture.
You cannot see the slide.
Yeah, the slides, sir.
I have no problem. I can see.
Oh.
How about you? How about everyone else?
I can see it.
I think your connection issue lah.
It's only on audio only mode. That is what is giving me on my screen, sir.
I think because of the connection speed or issue. But I
Can I opt out and come and reconnect, sir?
Yes. You try.
So let me leave the meeting and
Yeah. You try to log off and log in.
yes, sir. Thank you, sir. Sorry for the inconvenience.
Okay.
Yes, sir.
So it's okay. I give you 1 or 2 minutes.
Yes, sir. You can continue. I can view it now.
Okay, that's good. So I continue. Okay. So the pitot tube is basically a device used to measure the speed of the airplane during flight. Okay, it's look like a tube. Okay, facing against uh, the wind or the direction where during the fly. Okay, the the flying period. So basically, the pitot tube needs we will look into this principle in the flow measurement. Not going to go into detail here. So the thing is that it needs an or access against the wind while the airplane is flying. So it has a small opening, okay, at the front of the tube. The thing is that when the airplane is flying high, okay, 1,000 above the ground. So basically, it's the temperature is so cold. So what happens is there will be ice, okay, formation on the front of the tube, okay. So when there is ice formation on the front of the tube, it will block, okay, the flow, and then will you know aircraft, the system is very automatic. Okay, so this is a true story. Basically, pitot tube blocking cause the system of the airplane to produce a false info alarm, and then trigger. Okay, because it's too automatic, it's trigger, okay, everything, and then interrupt. So the pilot and then the co-pilot members, okay, didn't have enough time to change, and then they don't know what the problem. Okay, for where the system showing they are flying below the speed. Okay, so everything was changed, regulated wrongly, and accident happened. So to avoid, or when they discover that problem, so what they do, they install heating mechanism on the tube. Okay, so that heating mechanism help to warm up the pipe. Okay, so the technician out on the ground, when the airplane landed, they need to check whether that heating mechanism is working. So to expedite the inspection time, they can use a radiation thermometer, well, without having to if they use a contact uh, thermometer or solution, they have to climb, or they have to elevate using crane very close to the pitot tube. Okay, that will create a time delay, basically. So you need to clear up the area, and then, okay, everything must be make sure. But be using a radiation thermometer, so the technician don't have to, okay, have uh, to bring a lot, or like for example the crane. Okay, so that the time of inspection has been significantly reduced. Okay, so this is one of the application, okay, of thermal sensor in the aviation inspection as pulse production. Okay, I think this you can read, and also glass. I don't want to go through this. Okay, selection again. I think this same thing that I explained, or only a few addition lah to the selection guide. For example, here the range, okay, the range of the temperature that we want to measure. Okay, the accuracy, stability, response time, sensitivity, lifetime, of course, we have discussed about that. But vibration, of course, important. Okay, you need, okay, to check whether the thermal device has some effect on the vibration, like paper mill, for instance, just before. So paper mill, okay, they have a roller, and then they have moving mechanism, stamping, and then they have pressing. Okay, a lot of vibration, and then you need to check, or you need to make sure that the installation is properly fixed, so that the vibration may not be an effect to the measurement. Okay, now we look into, okay, thermocouple. Okay, basically thermocouple is a device, or based on the discovery of physicist Thomas Feedback, where um, the it they he discovered that when two dissimilar metal connected at both end, okay, to make two junction, and one of the end is heated, so a mole of current flow through the circuit. Okay, uh, so basically, based on the Seebeck effect, the conversion of heat difference can be made into electricity. So when two dissimilar, okay, metal wire okay, combine together, okay, create two junction, basically two junction. One is the measuring junction, one is the reference. Okay, and okay, reference, and then at the end of the open terminal will, okay, there will be EMF induced. Okay, so the output voltage, okay, has a relationship with the temperature difference between the measurement and reference junction. Okay, so so this is the simplest connection. Okay, the reference junction, okay, is basically close, or I mean is kept at 0 degrees Celsius, but in practical, two dissimilar junction is made something. Yeah, hang on. And so basically, thermocouple is consists of two dissimilar wire metal. Okay, okay, made into, connection made into two junction, like we can see here. One junction is made is used as a measuring junction. Okay, so whereas T1 is the measured temperature. Okay, so you are measuring an object or environment, and another junction is the reference junction, where the temperature is kept at constant constant level, or for example, in this case, is put into ice. Okay, made constant into 0 degrees Celsius. So the change of temperature, which is T1 minus T2, okay, will be proportional to the voltage or EMF induced between the open terminal lah. Okay, so will EMF, okay, will proportional to the EMF. Okay, so that's basically a basic construction of a thermocouple. Okay, consists of two dissimilar wire connect together to create two junction where the open part, will the temperature difference between the measuring junction and the reference junction, will induce EMF at the open terminal. So these are the thermocouple that has been packaged, uh, into the industrial devices. So, like for example, you have like a tube, or into metal casing, or something that is smaller that can be uh, screw into the surface. Okay, so these are the example of thermocouple. Uh, these are some of the advantages. They are basically self-powered, meaning that it is self-generate so this is a active sensor, which is does not require any no external power supply. So it does not require any external power supply, and it is relatively inexpensive as compared to other thermal sensing standard. It is based, the sensing or the structure is quite sturdy and tough because they are made of metals, wire, and alloy. Okay, and then it can be measure, or it can measure quite large temperature range from minus 70 degrees Celsius to 2700 degrees Celsius. Okay. Some of the advantages is here is listed as thermocouple output is relatively low voltage in range of millivolts. Okay, millivolts. That's okay. Perhaps the highest level it can reach, so that it is susceptible to noise. Uh, so some signal conditioning or filtering must be made to uh, to estimate the value of the thermocouple. Uh, the thermocouple temperature sensitivity is small, usually in the level of micro or millivolt per degree Celsius. It's quite small. So we need to use amplification, or we need to use instrumentation amplifier to make an accurate instrument. And then it require a cold junction compensation, like explained in the last slide. Sorry. Where we need to keep the reference temperature at a constant level. Okay? And then thermocouple are not as stable as other available temperature sensors. And then the accuracy, 1 degree Celsius means that that's the error. Okay, the error is around 1 degree Celsius of this is the reading of the reading. Okay, so cold junction is required. Okay, so the cold junction need to be properly insulated, insulation or regulate. They need special casing or fixture where the temperature is maintained at a fixed temperature. So there are other method like integrated cold junction compensation can be made, and also software programming for cold compensation. But I think the practical is using the control temperature block. Okay, these are the thermocouple type which are available in the industry. The the type represent the combination of metal, metal wire. For example, for type B, this is combination of platinum 30% and rhodium. So here you see the range is quite high, where it can reach at the high level it can reach 1800 degrees Celsius. Okay, but at the low level, it may not be accurate below 100 degrees Celsius. And then there are other thermocouple here, like E, which is combination of chromal constant, J, iron constant, K, chromal alumel, and rest that we can see here. Platinum is a bit expensive. Or combination of platinum is a bit expensive. Using the platinum, but if you can see here, by using the platinum, the range can be extended. Okay, as for example, for R, the range can be negative 870 degrees Celsius to 1450 degrees Celsius. Copper constant combination are the I mean it can one of the cheapest. Okay, and also like iron constant is cheap, JNT here in terms of the cost, but the range may not be significantly high as compared to other combination, especially as compared to platinum. Okay, these are some of the description of the thermocouple. For example, type K. This is the general purpose thermocouple. Type K. It's below the type J. So it is a general purpose. It's a trade-off between the cheapest and then the expensive in terms of cost. So one of the most type of thermocouple being used is type K. And then the temperature, good range, negative 700 degrees Celsius to 1200 degrees Celsius. Sensitivity is relatively low, but this is you can say medium range. Then we have like the chromal constant. This has a higher sensitivity, which might be well suited to low temperature, and it may be suitable to use in application where involve magnetic field generation. Okay, for example, in MRI machine, magnetic resonance imaging, the equipment. So that is basically a magnet, large magnet. So and then that magnet must be cooled down, okay, at a very low temperature to achieve a uh, superconductor characteristic or okay or condition. So to properly measure okay the temperature, okay, one of the equipment that we can use is thermocouple type E. Okay, so and then J has a limited range because it's made of like iron and constantan. Uh, so this is quite old. Uh, so it must not be used above 700 degrees Celsius, and it's made of iron, so the magnetic. Okay. So here we look into the comparison, okay, between the thermocouple, like in the statement before, type K is the general, whereas it has the medium or in terms of the sensitivity, okay, it's not low and then it's not high, it's in the middle range in terms of sensitivity. Okay, the sensitivity at the middle range. Okay. Okay, and then it can be measured at 1000 degrees Celsius. Okay. Type E has the highest sensitivity, but the range, okay, has a range of maximum measurable temperature, okay, is below than 1000, is around 1000, I think below 1600 degree Fahrenheit. Okay. As you can see the other comparison, like in the range of sensor thermocouple that use the combination of tungsten, it has very wide range, but low or poor sensitivity, and also the response. You see, the response is not nicely linear. Okay, as others thermocouple here, the response okay is some you can see it's proportional when the temperature difference is increasing, so the induced voltage is also increasing. But for these two like combination, it has a bit poor linearity, especially at the high range. Okay, it loses its linearity at the high range. It's just showing the response at the low temperature. Okay. uh, so they need also to consider the wire size of the thermocouple. If you use the larger size, so it means that it will increase the lifetime. Okay, but sensitivity will be compromised. Uh, okay, sensitivity is based on the material combination, but also the size may have effect. Okay, to the overall sensitivity. Okay, so you need to careful if you want the couple to stay or have a large lifetime. Okay, but the sensitivity may be a bit reduced. Okay, and then the probe uh, It is suggested that the thermocouple be immersed for a minimum distance equivalent to 4 times the outside diameter of the protection tube or well. Okay. So if the protection, okay, on the top, so they must be here. Okay. So if this is the diameter of the casing that protect the probe, okay, the distance here of the probe, okay, when you immerse into the system, okay, 4 times D, okay, to get a good measurement, okay. So that's how you determine how to immerse or install the thermocouple. uh, so the thermocouple, okay, must be close or proximate to the load or to the heat source. Okay. So it must be, if it's non-contact, it must be 1/3 of the distance from the object. This is the code of thermocouple in different countries. Okay. Um, so these are the application we see for the thermocouple. For example, for type T, it is used mainly in food processing, plastic molding, sub-zero condenser. Type J in uh, process that require furnaces, paper mill. So for type J, type K, okay, the general, okay, used in engine exhaust, glass manufacturing. Okay, that's where it usually found or used. So these are the precaution. So select, for example, you need to check the connection. If you need to increase the length of the lead from the thermocouple, so you must compensate or correct the thermocouple extension wire. And then the lead resistance must be minimized. Okay, to minimize and especially to improve the response time. Okay, and then decalibration, uh, noise, okay, can be minimized, okay, by twisting the cable together to cancel out the noise lah. Okay, so the wire basically twisted and okay, to cancel out the noise that uh, induced, okay, on the or on the wire or the connection. This one. Okay. Now, I there's a thermocouple table. So basically, this output of a thermocouple, it comes with the table. Okay. So the table, I will put later in the e-learning. So a table of thermocouple, okay, basically give the voltage that result for a particular type of thermocouple. Okay. So remember that the thermocouple, hang on. So thermocouple is okay. Basically, the voltage that is induced at the terminal is in proportional to the temperature difference between the measuring junction and the reference junction. Okay, so there is a okay in standard table. Okay, comes with this uh, every type of thermocouple. So the table okay basically shows okay the output of the voltage okay when at a certain temperature difference. Okay, but usually the table okay, is made or come okay, for the output is based on the temperature. Sorry, the reference junction is set at 0 degrees Celsius. Okay, reference. Okay, whereas T2 is 0 degrees Celsius. I'll show you an example. Okay. Okay, I'll show you this. Okay, this is table. Okay, represent okay the uh, output in millivolt. Okay, for range of temperature difference between the measurement junction and the reference junction. But in this table, the reference junction is set as the 0 degrees Celsius. Okay. Okay, so how do we okay come read this table? So we check at the left column, the left column, and then the top row. So left column and the top row, that is for uh, determining the temperature difference value. Okay, so we use that left column. Okay, left column here, and also the first row uh, to determine the value of the temperature. Then we will find the output in millivolt okay, based on the temperature okay, that we measure on the left column and then the top row. Okay, so for example, we see for a type J thermocouple at 210 degrees Celsius. T1 minus T2. Okay, at 0 degrees Celsius lah. Okay, so at 210 degrees Celsius, okay, we go to the table. Okay, we find, okay, 200. Okay, now we see that 210 degrees Celsius here. Okay, so we go left. Okay. Oh no, sorry. Yeah, so we look into this row, and then 200 plus 0 make up 210 uh, the temperature difference. So, and then we look into this column. Okay, look into this column. Okay, so 210 type J. So this is the value lah. Okay, the value. Sorry. So this is the value, the V value. According to this table, the value is 11.334. Okay, 11.334. So this is the two decimal place, 11.34 millivolt. Okay, so this table, okay, you help us to, okay, immediately find the value of the output, okay, based on the temperature difference value. Okay, next, if other way around or conversely, if the output is 4.768, okay, how do we find the temperature difference? But that is for type S. Okay, type S. So type S, I don't have the example here. Okay, we'll find the example and then put into the e-learning. Okay, so let's say we change it a little bit. Stay at type J. Or type J. If the voltage is 4.76, I don't not sure whether the exactly value 4.68. 4.68. 4.68. The point. Yeah. Yes, it's 0.468 millivolt. I think we got that. Oh, 0.768. 0.768. 0.7. There is no exact. Let's say we change that a little bit, the statement. The output for type J is 4.672. Let's see, we change that statement a little bit. Um, 0.678. 4.672. Type J. 4.672. So 80 plus 9, 89. Okay, let's say we change a little bit the statement. If we measure a 4.672 millivolt with type J at 0 degrees Celsius, so we can find from the table, okay, 4.672. Okay, then we look at the left. Okay, what's the value at the first column? 80. And then we look at the top, 9. So our temperature difference will be, okay, 80, 80 plus 9. Okay, 80 plus 9. So therefore, based on the table, okay, if we measure voltage of 4.7672 millivolt and type J at 0 degrees reference, we find from the table that the temperature will be 89 degrees Celsius. So that is the case, okay, where we directly find a specific value. But yeah, hang on. Okay, but in most cases, okay, the voltage does not fall exactly on the table value. So the value may be in between the value stated on the table. Okay, so we need to extrapolate or interpolate between the table value to find the desired value. Okay, so the value of the temperature can be found using the interpolation equation here. So the temperature measured equivalent to low temperature at low, okay, plus temperature at high minus temperature at low, divide by voltage at high minus voltage at low, multiply with the voltage measured minus voltage at low, okay, measured. Okay. So for example here, a voltage of 23.72 millivolt, okay, is measured with the type K thermocouple at 0 degrees reference. Find the temperature of the measurement junction. So we have our measure voltage here, 23.72 millivolt at for type K. Okay. Right. So we look at the table K. Okay, the value, the measured value 23.72 millivolt is somewhere here. Okay, as I mark. Okay, so that is VM. Okay, so here we need to determine the VL, VH, TL, and TH. Okay. Now, in this solution, what I choose, in this table, I choose this point as the VL and TH, and this point as the VH and TH. I can use this 2 point or this 2 point or this point or this point as long it is in between. Okay, so the value that we choose, okay, the VM is in between that 2 point because this is interpolation, linear interpolation. So if you choose this as a VLTL, in is supposed no problem, or you choose this as VH or TH, there not supposed to be any problem. Okay, but I basically choose the value here between here and here. Okay, so you can choose here, but I choose here. Okay, so in this case, our VL, okay, our VL low will be 23.629 millivolt, and our low TL. So our low TL, okay, we look at this 50, 50, and then look at the 0. So our TL is 5070 plus 0, okay, degrees Celsius. Okay, our VH, we choose here VH. 23.84 millivolt, and the TH 570 plus 5. Okay, 575. Okay, so we come back. So from the table, VL is 23.6, 2 decimal place millivolt, and our TL low 570 degrees Celsius, and our VH, okay, a higher voltage is 23.84 millivolt, and our TH is 575 degrees Celsius. Okay, so this is the point that I choose, in which this VL, VH, TL, and TH are between the VM, and then the VM value is, the measured value is 23.72 millivolt. Okay, so the measured temperature, okay, we do this extra interpolation. Okay, this equation TL, so will be 570 plus 575 minus 570 divide 23.84 minus 23.63, okay, millivolt, multiply with 23.72 millivolt minus 23.63 millivolt. So we get 570 plus 5 degrees Celsius divided by 0.2 watt, 0.09 millivolt. So we get the measured, okay, temperature, which is the difference between, yeah.
Please, Prof, if we look at the equation, we can see Tm equal to L plus TH minus TL over VH minus VL all of all cross VM minus VL. I think we can divide VM minus VL over VH minus VL and go with each other. Just will be TL plus TH minus TL. Why we do this?
No, this is VM, this is VH. How do you cross?
Okay. Yes. Thank you. Yes.
All right.
Yes. Just then my eyes. Okay.
It's okay. It's okay. So that is the case where the value is in between. The value is not stated directly on the table, so you need to do interpolation. So remember that the point that I choose, okay, is this point and this point. Okay, if you want to choose this as a VL and TH, I think you should get the same answer, and or you choose this one should get the same answer, because this linear interpolation is output, okay, on the table. Okay, no problem, as long as the value that you chose is okay. Basically, VM or TM is in between the uh, 2 points that you chose. Okay. Right. So in reverse situation, where the voltage in practical, basically you do measurement on the terminal. Okay, you do the measurement on the terminal, and then from that measurement on the terminal, you want to estimate what is the actual measurement or measuring temperature at T1. Okay, so and and most often the value will not exactly be on will not be exactly on the table. Again, you can rearrange. Okay, rearrange the formula here. Okay, rearrange the formula here. So then you get this formula. Okay. So the voltage measured lies between the higher voltage VH and lower voltage VL, which are on or in the table. Okay, so let's look at this example. Okay, type J still be maintained at 0 degree reference. Okay, find the voltage. Okay, find the voltage if the junction temperature is at negative 172 degrees Celsius. Let 100 type J. So we look at the negative 100, negative range. Okay, negative range. Okay, okay, they have to pay attention a little bit at the negative range. Okay. Negative 172. So the example said 100, negative 172. Okay. To read, okay, for the negative uh, range, okay, still we use the left column here, left column. Let's say negative 172. So here we have, okay, the initial temperature negative 100 on the table. So the output will be in between this row, in between this, okay, line, negative 100. Okay. So the example say negative 172. Okay. So the actual temperature to read, to find from the negative range. So you see the negative 172. Okay, look at the top column. So for negative range, you have to minus. Let's say, for example, this is negative 170. Okay, to find the exact output, you have to minus. Okay, so this is 2 actually. Okay, go down here. So actually, this point, okay, is the temperature is negative 170 minus 2 on the top. Okay, because okay, you see thermocouple output, okay, is linear. When the temperature difference is increasing, so the EMF should be increasing, and as well as when the temperature difference is decreasing, okay, the output voltage should be decreasing. Okay, decreasing on towards the negative value, the negative range. Okay, so this point, VM, is actually negative 172 minus 2, or not plus 2. Positive range, yes, you have 2 plus. Okay, for negative range, you have 2 minus. So take attention to here. This table, okay, you look at this example saying that, assume that at when the measured temperature at negative 172, what is VM? Assuming assume that the exact output is not on the table, but my example or table example here give the exact value here, negative 181. Okay, so basically we don't even have to use the formula, this formula lah. Whereas directly we can get the output is negative 7.18 millivolt. Okay, but okay, let's say we assume, let's make an assumption this point doesn't exist. Okay, this row doesn't exist. Okay, so let's choose 2 points, TL and TH. Okay, let's say 2 points TL and TH. I chose negative 100 degree Celsius here, oh sorry. Yeah, let's say I choose this point, whereas the TH negative 170 plus or minus 0, okay, minus 0, which is negative 170 degrees Celsius. So, and at the one other point, I choose this. Okay, whereas the T low is negative 170 Okay, when negative 170 minus 5. Okay, negative 175 degrees Celsius. So that is my TL. Okay, so TL VH is negative 7.265 and VH is 7.12 millivolt. Okay, so okay. Let's say we assume no, we assume we don't have the exact here. Let's assume. It's okay. We KIV here, we assume that it is not on the table. It's not available on the table. That we choose 2 points. Okay, one first point TH we chose negative 170 degrees Celsius and the correspond VH is negative 7.12 millivolt. Okay, and the TL is negative 175 degrees Celsius and the correspond low voltage is at negative 7.27 millivolt. Okay, so we use this formula PM. So in my calculation, I get negative 0.18 millivolt, which is the same okay on the table. So this proves that this interpolation equation basically can be used if the value on the table is not available. Okay, right. So we had take a break, 30-minute break. We will resume at
Doctor,
yeah yes
what if the reference junction is not zero?
yeah this example later.
Okay, later. Sorry.
It's okay. We're going to cover that later. No problem. Right. So we take 30-minute break. So we'll resume. What's my time? 10:50 at 11:20.
20.
Okay.
Okay, thank you.
Right. We'll resume our class today. So, as mentioned or asked by student, what if the reference junction is increased? Okay, rather than, okay, for example, the reference junction stay at 0 degrees Celsius. So it have been increased to a different value. It could be going to direct at any, there's a two possibility. It could be, the reference junction could be less, it could be increased than 0 degrees Celsius. But in a practical aspect, if you want to maintain the or make the reference to be at negative degrees Celsius range is not practical. Okay. So the practical thing may happen, the reference junction temperature could be increased to higher value. For instance, okay, in the example at 20 degrees Celsius, it is possible to use the standard tables, okay, to find, okay, the output if the reference temperature has increased. So basically, you need to remember that the voltage is basically proportional to the difference between reference and measurement junction temperature. So if there is a increase, okay, on the reference temperature, for example, in this graph on the bottom right here, this graph, okay, shows how the response, okay, the outputs shift or slide down when the reference has increased. Reference value has increased to 20 degree Celsius. So basically, all the values, okay, all the values has been reduced, okay, when the reference temperature is increased. Okay, so the basically for all the value, there will be a correction factor. So in this case, if the correction factor is 1.02 millivolt, okay, for example, okay, you have a output, given output, okay, then you want to, but the reference is increased by 20 degrees Celsius. So how do you use the table? The table is for 0 degrees Celsius reference. So the step is use the table, find the reference value or find the output value, okay, the output value at 0 degrees Celsius, okay, and then find the output, the output when the temperature is 20 degrees Celsius correspond to 0 degree, and then that value, this correction value, you subtract. Okay, remember when the reference value increase, so basically the output, all the output, okay, is shift down, okay, to a correction offset. Okay. Okay, so for example, okay, a type J thermocouple with 25 reference is used to measure oven temperature from 30 degrees Celsius to 300 degrees Celsius to 400 degrees Celsius. What voltage correspond to this temperature? Okay, so okay, but let's see. Okay. So remember that the principle of thermocouple, Okay, two dissimilar wire combined together to create two junctions. One junction is used as a measuring junction, and then the reference is set at constant value. So the output at the terminal, the EMF will be in proportional to the temperature difference T1 and T2. Okay, so in given standard table, the reference value is at 0 degrees Celsius. For in this case, okay, T2 has been increased to 25 degrees Celsius. So, what is the voltage output at 300 degrees Celsius and 400 degrees Celsius? Okay, so since this reference is not 0 degrees Celsius, so a correction factor must be applied to the table voltages. Okay, so in this case, okay, all the output has shift down. Okay, but our table or standard table shows the output for 0 degrees Celsius reference junction. Okay, so that correction factor is simply the voltage for a temperature or is simply the table voltage for a temperature of 25 degrees Celsius. That is the reference. Okay, so means the correction factor we write down like this. The voltage output for J, okay, junction, this means that the voltage output based on the table with the reference 0, and we write down here 25, okay, degree. So this is the correction factor. Okay, we look at the table. Type J, 25, 25, 25, 20. So look at this direction, and 20 plus 5 is the positive label. Okay, look at this direction on the top row. So we get this is the intersection. So the value is 1.28 millivolt. So that's the correction factor value, 1.28 millivolt. Okay. Okay, so this is the correction factor. Okay, correction factor 1.28. Okay, so from the table we now find the voltage for 300 and 400 degrees Celsius at 0. Okay, V output if the junction is at 0 degrees Celsius. What is the if the reference is at 0 degrees Celsius, and if the T1 is at 300, you can check from the table. I just write it down directly. Supposed to answer 16.33 millivolt, and the
Doctor,
yes.
I a bit lost how you come up with 1.28. Sorry.
Okay, so this is the correction factor. Okay, the okay, we need to find, so the reference value, okay, has increased from 0 to 25 degrees Celsius, isn't it? Okay, so that is basically the value that we're going to use for the correction factor. Okay, so this J, you see the output at 25 degrees Celsius, this is the correction factor. So this is the value where we're going to use to as a correction factor for every uh, range. Okay, range. That in this case, there are two value that you want to know the output at 300 degrees Celsius and 400 degrees Celsius. Okay, but on the table, if we find directly the value for 300 and 400 degrees Celsius, that is actually correspond to the junction if it is at 0 degrees Celsius. Okay, so we need to apply some correction factor on the output value. So first, you need to find the correction factor value. Okay, correction factor value here. Okay, so the correction factor value is actually the output. Okay, the output. Okay, at 25 degrees Celsius. Are you following? This correction factor.
Okay, yes.
Okay, so go to the table, find the output at 25 25 degrees Celsius. Okay, look at the tables, it's 20 plus 5. Okay, so this is the correction factor value, 1.28 millivolt. And then we hold that value. That value is actually representing the shift or the offset level. Okay, when the reference value has increased. Are you following?
Okay, thank you, Doctor.
Okay. So the first step is to find the offset value or the correction factor value based on the standard table. Okay, so go
Hello,
to the
doctor.
standard table. Yeah.
So if let's say the correction factor of the value, if 25 or 26 degrees, so we need to choose 26.
Okay, if 26, is it on the table?
Yeah.
So this is 26.
Okay.
So 20 plus 6 is 1.33. But it will be a bit tricky when, okay, let's say 25.5. So
Yeah. So
you need to do interpolation.
I need to do interpolation.
Interpolation, this. Interpolation.
Oh,
Okay. So you need to do the interpolation. But in this case, the output or the correction factor, okay, where is directly from the table. Okay. So you hold this correction factor first value. So use this as a correction factor. So okay, this correction factor value is not the value of T1 minus T2. Okay, this correction factor denotes the value, the offset. This offset. Okay.
okay.
All this offset. Okay, that is the offset value. This is the offset value. So at all value, this is the value the offset will have will have to taken into the consideration. Okay. Okay. Next, what is the output when the temperature at 300 degrees Celsius, 400 degrees Celsius? Okay, remember that our actual reference value has increased to 25 degrees Celsius. So the second step is to find the output at 300 degrees Celsius when the junction is at 0. Okay. So let's say, okay, we go through again. Let's say 300 degrees Celsius. Go to the table. 300, 300, go down. 30. Okay, 30 here, this way, and then plus 0 this way. So this is the value, so 16.38. Okay, 16.38 or 16.33 millivolt. Okay, 16.33. Okay, so this is the output when the reference is at 0. Okay, let's say lah this. Okay, this is the output at 0 when the reference sorry. Yeah, this is the output. Let's say this is the output at 300 degrees Celsius. Okay. 300 degrees Celsius, and then the reference at 0 degrees Celsius. Okay. But remember that our reference has increased. Okay. So there's an offset we must apply. Okay. So at any point, and but this question asked to find the other value lah. Okay, we put 400. 400 from the table you should get 21.85 millivolt. Okay, so finally the output, the actual output when the junction has increased to 25 millivolt for 300 degrees Celsius, okay, is equivalent to, okay, from the table for 300 degrees Celsius minus the correction factor. Okay, so it will be 16.33 millivolt minus 1.28 millivolt. So that will be 15.05 millivolt. So look at this. So this is the junction at 0. So due to the correction factor, so the value at this point has reduced, okay, to this. So we need to minus the offset or the correction factor, okay, because the temperature has increased. I mean, the reference junction temperature has increased. Okay, similar to 400. Okay, so VJ0 at 400 degrees Celsius minus the offset value of 225. So this should get 20.57 millivolts. So for 400 of course happen beyond here. Let's say 400. This is at junction reference junction 0. So when the reference has increased, okay, we must apply an offset. Okay, so that is in the case when the reference junction is, okay, reference junction is changed. Okay, it's changed. To me, if one to ask anything on this, I will not put the reference junction at negative value, negative, let's say negative 20, because it's not practical. Okay, in practical point of view, how is difficult, if it's difficult for you to set the reference junction at negative value. 0 degrees Celsius is already challenging. Okay, but maybe the logical increase is at the positive lah, or for example at 25 degrees Celsius is the room temperature. Okay, room temperature, so it's much more doable. So in the practical side, okay. So I wouldn't ask for what will happen at negative side, but you can see if they're negative. Okay, so the curve, okay, will increase nah. And but how come, okay, it happen or it increase, okay? Right.
Doctor,
Yes.
can guide us how to get the 16.33 millivolt from the table?
How? You this value?
The
Yeah.
16.33 millivolt. Yeah, from the table, how to,
Get.
yeah,
Okay, so this one,
yeah,
okay, from the table, but the output or the T1 minus 2 at 300 degrees Celsius. So you go to the table. So basically you want to find the voltage 300. The what is the output when T1 minus T2 is 300? Okay.
okay.
So look at the column, first column.
So I need to take 300 and 400.
Okay, so no, 300 here is okay. This is the first, the first line.
Okay,
Okay, so the value will be in between this and somewhere here lah. Okay, there. Okay, you get it? Let me do something else. Mark. Okay, the value should be somewhere here. You see?
okay,
Okay, but you need to look at the top row here. 300 plus to get 300 plus
0.
0. Okay, so this is okay, 0. So cross, oh, cannot do that. So you go down here until this is the interception.
Okay,
Okay, so that's the value
very
16.38. That's the
mm,
positive side.
okay.
All right. Okay, so that's how to get the
Mm,
16.338. Similarly, that's how you get 400. Right. So I hope that is clear. Take some time to like digest the information. But I think the information on the slide is already clear, at least to me. Okay. And also I will update the slide. I will put the updated slide under the current slide of this lesson 3 at the e-learning. All right. So that's finish discussion about thermocouple. We move on to thermistor. Thermistor is also a sensing thermal device. So the principle is based on semiconductor material, typically mixture of metal oxide. So it is a family of semiconductor device, and it is significantly higher sensitivity as compared to thermocouple. There are some characteristics that we need to look into or to observe. For instance, the thermistor has a very non-linear characteristic. Okay, example in this graph on the left here shows that the resistance change of the thermistor versus the temperature change is basically exponentially decrease. Okay, the resistance is basically exponentially decrease when the temperature is increasing. But that's the characteristic, and it came in many shapes like probe, rod shape wafer and disc, and the size is relatively smaller as compared to thermocouple, and the temperature range is around negative 100 degrees Celsius to 300 degrees Celsius. And normally this sensor need to be used with extra or certain circuitry or signal conditioning circuit. It cannot be used directly because the temperature, the resistance change depend on the temperature, and output that we measure usually in electrical signal. So we need to put or use the thermistor into a circuit with power supply. These are the sizes and form of the thermistor. It could be as small as a match stick tip, and it can be into probe, but normally it's small. For example, this micro beta chip probe thermistor. So there are two types: the positive temperature coefficient and negative temperature coefficient. So positive, basically the change of resistance with the temperature change, it increase exponentially. But for PTC, as we seen before, okay, the resistance is exponentially decrease. Okay, they can be very small because it can be used in very small spaces. Okay, this is okay. Okay, so the application like this thermistor is for lab research, especially in equipment or setup where we need to measure very small area. It is inside, for example, in our electrical appliances lah, like our laptop, inside our the gadget, because it can be integrated directly into, like for example, the CPU board. Okay, so whatever temperature change can be measured directly. These are the construction for you to look into. Like for example, this one NTC thermistor, negative type, negative temperature coefficient thermistor, basically sealed with glass, okay, at the tip. This one is same material like common passive capacitor. It is seen or can be found inside the home appliances like the fridge, air conditioner. So it is integrated with the circuit board or the system. This one like can be installed on the board, printed circuit board as a surface mount device. We go, and the characteristic, the sensitivity is very high, measured in resistance per degree Celsius. And then the construction based on these bead and rods, but the range often limited between negative 100 degrees Celsius to 300 degrees Celsius. Okay, the limitation, okay, because of the material is based on semiconductor material. Semiconductor material is a low low coefficient material, so it cannot withstand extreme temperature, and also the protective material like plastic, epoxy or Teflon. Epoxy and Teflon, the same material that is used to package the common passive capacitor. So they're not suitable for very extreme temperature. Okay. And then the response time depend on the material. A different material, okay, response time, okay, will determine the response time. Like for example, if it is immersed in the liquid, the response time will be faster because the uh, thermal transfer is much faster in liquid. But if it is in air, it will take about 10 seconds before it reach the final value. Okay, and when it is encapsulated with much thicker material, so it will take more time. The signal conditioning is common one is using a Wheatstone bridge. I mean, that's the more accurate method. But the least accurate is using voltage divider. Advantage is small, and then react fast in temperature. And then the output, the output resistance is high, means that you get a better resolution for small temperature change. And then this resolution is much higher than RTD, and also they are much cheaper than RTD or even thermocouple. They are much cheaper. But we look at the disadvantage. They are non-linear. So because of the non-linearity, it cannot be because it's highly non-linear. So it cannot be suitable for big temperature range. So it is very good for small temperature range, smaller temperature range. And also it is limited to much lower temperature exposure than RTD or thermocouple. And also if the device is smaller in dimension, so careful must be considered in giving powering up the device. So you have to adjust the power level, otherwise the semiconductor device will be easily perish or malfunction due to the high current flow through the thermistor. Application, I think I have show before. This is the other application where the thermistor is used as the level indicator, whereas basically this thermistor is in parallel with the alarm circuit. Okay, and then the alarm circuit basically have a solenoid which control the alarm. Okay, relay, basically a relay with control the contact, whether set off or set on. And then the solenoid is in parallel or in series with the capacitor. So the power is given to the circuit, current is given to the circuit. And then the thermistor is basically, let's say, okay, thermistor is somewhere at the top level, okay, and let's say inside the tank, okay, thermistor, and then water level, okay, will rise, okay, according to the water flow inside the tank. So when the thermistor is exposed to air, okay, so when it's exposed to air, basically temperature is air. Let's say this T1, this is T2. When it is air, T1 is larger than T2 lah. Is the T2 water temperature is much colder than the air. Okay, so in this condition, air temperature is high, so resistance is high here. The thermistor, okay, R is high. So when resistance is high, so less current will go to this path, and more current will go to the solenoid. Okay, this is a solenoid or relay. So and for DC voltage, okay, and T, so the capacitor here is like a closed circuit. Okay, closed circuit. Okay, so current will flow more to this direction when at air. Okay, but when the water rise and reach to the level of level of the thermistor, okay, water, so basically T2, the temperature of the thermistor will be T2, thus causing the resistance. Okay, you see there is a PTC when, sorry, it depends on the type of the thermistor. In this case, maybe use, okay, thermistor in this case, okay, I think wrong direction. When T1 is higher than T2 for this temperature, okay, basically high temperature, like let's say T2 is here, T1 is here. Okay, so let's see, resistance is high. So resistance is high, so less current will flow here, with more current flow here. Okay, current when this is high, I 0 lah, or close to 0. More current will flow into the alarm circuit here, solenoid. So energize the relay. So alarm with no set off. Okay, alarm system. So alarm will still off. Okay. Okay, when the water rise, okay, water rise. I think I'm giving the wrong. I think it's supposed to be here. But anyway, I think let's skip this example lah. Okay, this thermistor, different package. Okay, like it come with the handheld device. Okay, let's look at this example. Let me down. So, thermistor basically characterize according to their type, base resistance. Okay, base resistance. So in this example, the thermistor has a base type of 4 kilo ohm. So this curve showing a thermistor with different base value like 100K, 15K, and so on. But in this example, the thermistor here is the base, okay, resistor is 4 kilo ohm. So 4 kilo ohm curve is in the middle here, okay. So we use the curve in the middle to find the actual resistance of the thermistor at certain temperature. Okay. So this thermistor is used in the voltage divider circuit. Okay, there's a ammeter with the internal resistance of 3 ohm, and also and also here is a variable resistor RC, okay, set at 170, oh sorry, as 17 ohm. The supply is 15 volt. So here the ammeter have an internal resistance of 3 ohm. So find the meter reading for 77 degree Fahrenheit and 150 degree Fahrenheit. Okay, so from the graph, we need to find the resistance at 77 degree Fahrenheit. So how we find it? Okay, we look at the temperature here. We'll find the 77 at 4. Look at the 4K curve here. So the value of 77, okay, maybe somewhere here. 77. We go up. Okay, so maybe this is the interception at the 4 kilo ohm curve. So we look at the value here. This is a semi-log. Y is in log scale. 1,000. This is basically 2,000, 3,000, and this is basically 4,000. So the output is 4K. So the current I we use the KVL. I equivalent to 15 volt divided by the total resistance of the circuit. Okay, 4K is from the thermistor. This is from the variable resistor here. And 3 ohm is from the ammeter. So we get 3.73 milliamp. Okay. So what happened when the resistance or the temperature increase? Okay, basically when the temperature increase, so temperature increase. So what is the resistance at 77? So this is not the answer. So at 150. What is at 150? And resistance at 150 is here. 150. You go here. We get here. Is it here? Only here. No. Sorry. This is 150. Around here. It could be 1K. Okay, 1K, or in this answer is 950 ohm. It's very close, but I think if you write down 100 or 1000 ohm is okay, acceptable. So when the current okay, current of the whole circuit when the temperature increase, okay, see the current is increased. Another thermal sensing device is resistant temperature detector or RTD. So this thermal sensing device is based on metal wire basically, and this metal wire characteristic basically the resistance uh, will change when the temperature that exposed to the metal wire is increased. So it's basically based on metal wire, and RTD has a slow response time between 0.5 to 5 seconds. So this response time range is because of the thermal conductivity in bringing the device into thermal equilibrium with its environment or to the object that it's want to measure the temperature. Okay. So we'll see later the construction of the metal, construction of the RTD, whereas it consists of several layers, and the common types of metal wire used to construct RTD are basically platinum, copper, nickel, and the combination of nickel wire. We will look into the comparisons between these metal wires. So basically, copper and nickel, okay, operate at lower temperature ranges, and they are less expensive than platinum. Platinum is less abundant as compared to the other metal, and also platinum is quite expensive. If I'm not mistaken, it's much more expensive than gold. So the requirement for resistance used in RTD are larger sensitivity, high resistivity. First is the larger sensitivity, where we want to have a good output response change, okay, with a given input response change. And high resistivity of the wire to ensure small wire length for high resistance is this in terms of converting the resistance into output voltage. So the high resistance value of the RTD helps to basically reduce the loading effect in the measurement. Okay, and also they are used because of the linearity between temperature and resistance. So the basic construction as can be seen here, the cross section of the RTD. Basically, the sensing element is based on a metal wire, okay, and it is coil at one end and bundle the wire that is coiled and bundled close together, and basically the other ends okay, of the metal wire is connected to lead wire. So the sensing part of the wire that made into set of coils, they are insulated, okay, with two layers. The first layers is ceramic support. Okay, basically it's filled with ceramic support, and the wire is basically inside the ceramic support, and the outer protective layer, this is basically a sheath or an insulator made of glass, ceramic, or mica. So you see that this RTD has several layers. Okay. So the thermal conductivity will take some time before it can penetrate the sheath, the ceramic support, and into the then reach to the sensing element. So platinum element predominantly mainly used because of their wider range. And platinum, if you consider platinum, it is the most repeatable and stable of all metals. Means that it can retain the output for a given input. If you apply the input many times, and then also the platinum can be exposed to temperature up to 1500 degrees Celsius. Okay. So on the platinum is less reactive to chemical, okay, especially to the support. So when things or the sensor is heat up, so platinum basically less likely to absorb some of the impurity. So the platinum, in terms of the range, are large, between negative 263 degrees Celsius to 1545 degrees Celsius, but the sensitivity is at moderate level. For copper and nickel, their temperature range is much less as compared to platinum. You see, even like nickel, okay, maximum is 316 degrees Celsius. Copper is much less, but their sensitivity is basically much bigger. And then the sensitivity is, the unit of the sensitivity is, okay, the output of the resistor over the reference resistor, the ratio, okay, divided by the temperature. So this is the sensitivity unit for RTD platinum. Okay, so these are the characteristic for platinum. So you see that the output change of the output the resistance change, okay, is around 0.4 ohm if the temperature that is measured, okay, at every degree Celsius change. Okay. So 100 is basically, okay, the reference, okay, and RT also the change. And then the response times is basically slow between 0.5 to 5 ohm. Okay. Because of the, as I mentioned before, due to the thermal conductivity, so the temperature takes time to absorb into, okay, fully absorb into the sensor, and whereas the sensing element is in the middle of the structure. Oh, okay. And signal conditioning circuit that can be used, like bridge circuit or differential amplifier, okay, which we will go into or look into in the next chapter. So the limitation is that RTD rarely used beyond 660 degrees Celsius. So at this range, okay, we have to go something much, something or thermal sensing that can sense higher temperature. And we have looked into, basically we have looked into thermocouples. Okay, that can be an alternative. So the reason is that at very high temperature, okay, so the metal basically will partly, okay, will basically heat up at extreme temperature, and then will, uh, inevitably absorb the contamination, okay, coming from the metal sheath. So basically metal sheath will be partly melted. Basically some of the particle will be absorbed into the core, okay, and then fuse with the sensing element. So in some application, they will change the sheath or the insulator from metal to glass. Okay, but care must be carefully given when handling the RTD with glass insulator or sheath. So as comparison to thermistor, RTD are less sensitive, whereas the small temperature change have a slower response. Yeah, but thermistor we have discussed, it has a smaller temperature range. It's for narrow range application. But RTD, okay, is for much bigger. But if we want to have a higher output change, okay, at high temperature, we go for RTD. So these are the list of the advantages. Okay, temperature range can be below 260 degrees Celsius to 850 degrees Celsius. Okay, good repeatability and stability, and the sensitivity. Okay, it can provide much larger than thermocouple. Okay, but okay, less than thermistor. But thermistor is for different application. Linearity is much better as compared to thermocouple and thermistor. So the linearity can be further improved, okay, by using proper signal conditioning method. And then in terms of the cost, it's much effective. And also RTD, it was constructed based on industrial standard IEC 74759, for instance. So when there is a standard, so they can ensure that the manufacturing has follow good practice or good rules where a lot of elements or condition have been considered, like safety, repeatability, stability or reproducibility, accuracy, and most importantly, uh, when we have standard, means that it is a part of traceability. We will look into a concept of traceability later. Yeah, disadvantage of RTD. So it is not an active sensor, whereas the conversion of the thermal energy to output voltage have to go through a signal condition or a conditioning circuit. Okay, the simplest conditioning circuit we can construct is using voltage divider, for instance. That's the simplest one. And then we can also resort or use Western bleach and so on. So these are the characteristic of the RTD sensing element. Okay. But first, we look into here on the chart here, the RTD characteristic. So it is basically plotted based on R over R out, R or R naught. Okay. Okay, is basically R is the uh, resistance, the actual uh, resistance of the RTD at a given temperature, and R naught is the basically reference reference resistance. Okay. And it is this is the output, and the input is temperature. So the sensitivity is basically the change of this variable over which is the output, and then or divide by the input, which is the temperature, the actual temperature of the object. So as you can see here, platinum has a moderate sensitivity, and then it has a good linearity. Okay. Copper and nickel has a higher sensitivity, but it suffer non-linearity, especially at high temperature. Okay. So the relationship the equation of the RTD is given by this formula. So RT is the basically the resistance of the or the output of the RTD equals to RT naught, or RT naught is basically the resistance at reference temperature, and usually we take that that as a midpoint temperature. Okay. And T is basically the difference temperature. Okay, T minus T naught. So this is supposed to be the delta T, delta T, delta T. Okay. And alpha, beta, and delta is basically the temperature coefficient. So you see that in the this part of the equation, 1 plus alpha delta T. So alpha is the linear coefficient or the linear sensitivity, and beta is the cube square. Oh, sorry, the square or the quadratic coefficient. Okay, and delta is basically the cube coefficient. So for platinum, okay, alpha coefficient is much bigger than beta and delta. But for copper and nickel, so basically the beta and delta is much more significant than the alpha. So therefore the output here, you can see is much more non-linear at high temperature. Okay, so for this is an example, same example of the metal resistance versus temperature. Okay, versus temperature. Okay, so find the linear approximation. Basically find the linear approximation that represent the equation, basically to find uh, this equation. Okay, oh, sorry. So we need to find RT equivalent to R T naught 1 plus alpha delta T, or we can write that like this: RT naught 1 plus alpha T minus T naught. Okay, so we need to find few parameter here. Okay, like RT naught, alpha, and T naught. Okay, so like I mentioned before, RT naught is the reference, and usually it is choose at the basically at the reference. Okay, reference. We can choose at the reference. So reference is usually at the midpoint. So let's say we have this 60, 60, 65, 70, 75, 80, 85, and 90. So there are 7 points. So since we have 7 points, okay, we can conclude that 75 is at the center. Okay, so we can choose basically T naught as 75 degree Fahrenheit. Okay, and R T naught to be 110.2. Okay. Okay, so we need to find the alpha. You see alpha. Okay, let's say the temperature here from 60 to 90. And here on this part is R, or the the resistance of the actual resistance of the RTD. Okay, so at 60 is around 106.0, and at 90 is 112.2. Okay, right. Okay, so the alpha, remember the alpha is R over RT naught over, or me the change, okay, over delta T, okay, the alpha. So in this, okay, here is R, so means that, okay, we have to divide this with RT naught, the reference. So RT naught, okay. So we will have to include the RT naught in the calculation. So okay, basically in the calculation, or we can approximate it's like this lah, delta R, okay, over delta T, multiply with RT naught. Okay, so we can approximate, okay, the alpha like this. So alpha, the change of the resistance over the change of temperature, multiply with 1 over RT naught. So let's say we choose this as our first point, and then this is our second point. So R1 minus R2 over T1 minus T2 multiply with RT naught. So we get 112.2 minus 106, okay, over 90 minus 60 multiply with 1 over 110.2. So alpha is equals to 0.001875. Okay, the unit is 1 over degree Fahrenheit. That's the unit. So finally, okay, our equation RT is equivalent to R110.21 plus 0.001875. Okay, multiply with T minus 75. Okay, so that's the equation. Oh, okay, so that's the equation to, okay, look at the RTD approximation.
Assalamu alaikum.
Salam.
Please, Prof, just I ask if this is recorded or no.
Pardon? Again? Come again?
Yes, this lecture or this class is recorded or no?
Yes?
Okay, okay. Can we get it in e-learning, yes?
Yeah, of course. Okay, so that's how we approximate the equation for RTD based on the characteristic of a metal resistant, temperature versus the resistant output. And RTD, these are the some different construction of RTD. It can be as small as a thin film platinum. For this construction, I think I leave it to you to read. The information. This also some other RTD probe assemblies available on the market, and then the size, the variation, goes on, depending on the application, right? So do we compare the thermal sensor between RTD, thermocouple, and thermistor? So first we look into the temperature range. Thermocouple has the highest range possible, between negative 200 degrees Celsius to 1800 degrees Celsius. Thermistor is the smallest. RTD is at the medium range. In terms of cost, as you can see here, in terms of the cost, RTD cost is basically moderate, thermocouple low, and thermistor is low. But in terms of the whole system, thermocouple is the highest because it's require much dedicated signal conditioning circuit. As for RTD and thermistor, the basically the system cost is low. But big RTD and thermistor, we have to apply power. We have to supply power source because they are passive sensors. In terms of the stability, RTD is the best, thermocouple is low, thermistor is moderate. Sensitivity, thermistor is the best or the highest. But because they are good for narrow range, as specified below, and the sensitivity, for thermocouple is low and RTD is moderate. Linearity, RTD, through the linear approximation, they are the best if you consider the linear approximation. Thermocouple moderate, but thermistor has a very high linearity. So if you use thermistor, for the effect of nonlinearity is not that obvious or significant at narrow range. So which one we want to use? RTD in the industry, especially RTD can be the common, but few limitation if the temperature range is very high, so we have to go for thermocouple. Thermistor basically specific for medical applications, or home appliances, or So these are the other thermal sensor, okay, like for example bimetallic strip thermometer here. So I have to based on two different metal that expand at different rates when the temperature increase. So basically it will bend out okay when the temperature increase, so remove the contact. So it can be it is one of the common thing, okay, in the ovens, okay. This is based on mechanical movement. Okay, there's the other one that you can see. This the other application here you can go through. Okay, what wooden